Hello guys, welcome to Physics Grad. This is day 7 of daily quantum mechanics, and in this video we are going to continue with our examples on basis and components. So let's get started. So here I'm going to continue with our example of arrows in a plane and then go on to 2 cross 2 matrices. Alright, so just to recall, you can just pause the video and see what we mean by the definition of dimension of a vector space and what you mean by or in this case the theorem which says that you can express any random vector v in the vector space as a linear combination of n linearly independent vectors if the dimension of the vector space is n, and this is the definition of basis. And then we had also seen that we can define components with respect to a given basis, and we also proved a theorem wherein we said that the components is unique for a given basis. And we also saw what the general rule for adding two vectors in terms of their components, and also how to perform scalar multiplication using the component representation. Okay, so in the last video I had already discussed an example with respect to arrows in a 2D plane, but that was a bit general and I did not discuss any specific case as such. So I feel that it was not convincing enough, so I am going to do it once again, but with the more specific case in this problem. So here we are going to take some vector v in 2D which has a length of 10 units, and I'm going to consider two linearly independent vectors 1 and 2 which have unit lengths. And as we had seen in one of the previous videos, for arrows in a 2D plane, the dimension of that vector space is 2. That means we can at most choose two linearly independent vectors and they form the basis. So in this particular case, our choice of basis is the vectors 1 and 2 as represented in this image, and they're both unit vectors. And now what I want to do is express the vector v in terms of this basis, okay? Or in other words, I want to find the components of v with respect to the basis which consists of the vectors 1 and 2. And you all know how to do this. It's simple trigonometry problem. So all you need to do is find complete the parallelogram with respect to the vectors 1 and 2 such that the vector v becomes the diagonal, which means the length of these two sides must be chosen appropriately, which means we need to multiply vector 1 and vector 2 with appropriate constants. And how do we get that? We simply get that by using simple trigonometry. And so this length, for example, is nothing but the length of this arrow times cos of this angle. So that is 10 cos 60, which is 5 root 3. Similarly, the length of this side is going to be 10 sin 60, which is just 5. Okay, so we are expressing the vector v in terms of a basis expansion, where the basis vectors are the vectors 1 and 2 represented here, which have unit length. And since they have unit length, we can directly multiply that particular vector with the length of the side of the parallelogram, which is appropriate. So that is what I have done here. So therefore, with respect to this particular basis, the components are 5 root 3 and 5. Okay. So now let us see, let us try to express the same vector v as in terms of a different basis rather than the basis 1 and 2 which was shown here. So in this particular case, we are going to consider the basis vectors as these vectors 3 and 4, which are obviously not the same as vectors 1 and 2, because first of all they are not perpendicular, okay, because they make 45 plus 30, which is not equal to 90. So they are not perpendicular set of vectors. and also they are not unit vectors. So in this particular case, the length of vector 3, I have taken it to be 2 units and length of vector 4 to be 3 units. And now I want to express the vector v in terms of this basis, or in other words, I want to find the component of vector v with respect to the basis vectors 3 and 4. So what will that be? So again, I complete the parallelogram and I need to find these two lengths. And then what I need to do is multiply the vectors 4 and 3 in such a way that with numbers in such a way that their length correspond to the length of these sides of the parallelogram. So the way to do that is basically, first we need to reduce this vector to a unit vector, which is what is being done here. So this is where it is being done. So for example, vector 3 has the length of 2 units. So I divide vector 3 by 2 in order to make it a unit vector. And then I multiply it with the length of the side of the parallelogram appropriately, which is AB. And same thing is done for vector 4. So wherein we take the vector 4 divided by the length of that vector, making it a unit vector. So this particular guy is a unit vector now. And AD is nothing but the length of this side of the parallelogram, which we need to figure out. So at the end, what we will get is that the component with respect to vector 3 will be AB by 2, and the component with respect to vector 4 will be AD by 3. So now it becomes just a simple trigonometry problem to figure out what the side lengths AB and AD are. Now I'm not going to explain that in detail, but however I have calculated over here. You can just pause the video and go through the calculation and convince yourself that this is the result that you get for AB and AD. So once we do that, by dividing it with the 2 and 3 appropriately, what we get is the following. So we can express V as 3.415 times vector 3 plus 2.415 times vector 4. So therefore, with respect to this particular basis, our components become 3.415 and 2.415, which was actually different as compared to the basis which we had chosen earlier, which are vector 1 and 2. So the main message here is that the choice of basis is very important, and that in turn will decide what are the components of the vector. So when you specify the components of a vector, you need to also specify the basis with respect to which the components are defined. So therefore, in this particular case, although these two expressions are giving you the same vector, however, you can see that their components are completely different, and the reason for that is that the choice of basis was different. Okay, so we can choose any basis. The choice of basis is not unique, but as long as we have a basis, we can express that vector as a linear combination of that basis, and once we choose a basis, there is a unique set of components using which we can expand that vector in that basis, which was a theorem that we had seen earlier. So with this, it should be clear to you what we mean by basis and components of a vector. All right, so basis of a vector space and components of a vector. Okay, next. Now we will consider the case of 2 cross 2 matrices. And just like how in the case of arrows we took two different bases, 1, 2 and 3, 4, here also we are going to consider two different bases. Okay, so the first basis is basically the 4 matrices which we had already seen, where only one of the entries is 1 and the rest are zeros. And the second basis, which also I had discussed in one of the previous videos, consists of these 4 matrices, okay, which are not just a single non-zero element and rest all being 0. This is some kind of a general 4 linearly independent vectors in this particular vector space. So with respect to these two bases, let us try to express a general vector, Okay, we saw that this is a general vector in the vector space M. So in terms of the basis 1, we can express this as A times the first basis vector, B times the second basis vector, C times the third, and D times the fourth. And in a similar way, we should be able to express the same vector in terms of the second basis, but now obviously the components are going to be different. Now how do we find these components? We just need to solve the equation for the corresponding uh, position of the numbers in this matrix. So for example, if you consider this particular equation, how I got that equation is that this A must be equal to V1 times 1, that is this guy, plus V2 times 0, which is this guy, plus V3 times 0, which is this guy, and V4 times 2, which is this guy, which must be equal to A. Okay, so in this manner you can write down 4 equations and there are 4 unknowns, which means you can solve for V1, V2, V3 in terms of A, B, C, D. So what you will get is that you will get some values for V1, V2, V3, V4, which will not be the same as A, B, C, D in this case. So again, what I am trying to say here is that by choosing different bases, your components will be different. However, both of these expansions represent the same vector, which is A, B, C, D. Okay. So now let us also see and take this example to realize that to add any two vectors, we just need to add their corresponding components. So this is easy to see if you consider the first basis, which consists so if you consider these bases, it is easy to see here that this matrix will be nothing but A1 times vector 1 plus B1 not plus plus B1 times vector 2 plus C1 times vector 3 and plus D1 times vector 4, whereas this is nothing but A2 times vector 1, B2 times vector 2, and basically their sum, which is equal to A1 plus A2, sorry, which is equal to A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2. Now this matrix in the same basis is nothing but this guy times the vector 1 plus this guy times vector 2 and so on. So this is not that hard to understand, you get my point. So similarly, if we had expressed this in the second basis, the corresponding components will be added to give up the result of this particular sum. Okay, so there's nothing complicated which is going on here, very simple and straightforward, and you can just try to work it out on your own and you should be able to understand if you have understood this particular example. So obviously by choosing different bases here, these terms are again going to be different because they are the components, and the components are going to be different when you choose different bases. So similarly, scalar multiplication means when you multiply this matrix with alpha, you are supposed to get this matrix, which is nothing but if you take the same basis, you are simply multiplying each of the components with the value alpha, which also we had seen in one of our earlier definitions and properties and so on. So with this, I would like to stop this video. I will see you on day 8. Thank you for watching. Take care.